Welcome to our new webinar with Cadence presenting, and we're happy to have you here. We will be releasing this recording after this webinar on HDL website. But today we have a special guest from Cadence uh, Design System, and that's Jeff Rohn. He's a group director, product management, and he will be presenting for us the tool flow for Cadence that integrates AI and agentic AI flow for chip design. And we're excited to have Cadence team support us with AI HDL and provide tool access for participants to be able to get the exposure to industry standard tools. More information about the tool access will be released hopefully next week. And this week we thought it would be a good idea to give you an introduction to these tools through this webinar. And next week, once you have the access, hopefully, you will have the basic and fundamental knowledge of how these tools work together and how this agentic AI flow that Cadence has can help you guys in your chip design journey. Um, all right, I think without further ado, Jeff, please go ahead. The floor is yours.
Thank you, Sohail. Again, my name is Jeff Rohn, and I head product management for Cadence's digital front-end tools. And that involves our synthesis solutions as well as some other adjacent products. So today I'm going to talk to you about a new technology, a new product. We released the first version in December of last year, and we've got subsequent versions kind of scheduled for this year and on into the future. So as the name implies, agentic AI overview, the product is very much an AI agentic solution, right? And it's focused on code generation, but code generation specifically for RTL design. So as you're probably aware, there's just a lot of kind of code generation activity in the market. I think it's safe to say that LLMs have kind of proven their ability to, assist to automate a lot of kind of manual code development tasks. But if you dig in, all the discussion is really around code development for software developers, right? So, generation of C++, generation of Python, and so forth. But there's beginning to be some discussion on applying this technology to RTL design, and there are some emerging kind of standardization efforts and open source benchmarking efforts that are designed to kind of inject some way to kind of quantify the goodness of these new technologies. Suffice it to say that where we are today is despite the amazing success that LLMs have had in assisting the software development community, we're still very, very early on the hardware side. And in this presentation, I'll go into exactly why that is, and more importantly, what Cadence is doing with our technology to kind of overcome some of these kind of initial barriers to success. So with that, let me go ahead and get underway. We'll start with kind of just a look at our journey as we see it to autonomous design. I mean, we see, and I think the industry would uniformly agree that where things are headed is this full autonomy, right? Where you can input a natural language description of something, and then you can have these agentic workflows that either call AI engine or call other task-specific tools to do parts of that overall composite flow. A lot of activity going on. We're not there yet, clearly. Will we ever get to a point where you can enter a specification and have it do all the, in an automated fashion, all the chip design work? Remains to be seen, but independent of whether we reach that goal or not, we're going to get close. And in getting close, we'll deliver greater productivity. So what this slide breaks down is the 5 levels of autonomous design, or getting to autonomous design, if you will, or AI technology. The first level we defined as optimization AI, and you can think of this as really reinforcement learning solutions. Hugely different from LLMs. What reinforcement learning solutions do is they conduct a number of trials, and based on the results of those trials, they update their learning model, and the goal is to be able to more efficiently traverse a solution space. So we have a product that's called Cadence Cerebrus, and we've attached that or integrated it to all of our implementation solutions. It's performed very well. We've had well over 1,000 tape outs. Tape outs a measure of success because that marks the completion stage of a design when that design is handed off for manufacture. But suffice it to say that um, um, practically all of our top 20 customers are using this technology, so it's very well proven. The next stage is conversational LLMs. And you can think of this as like chatbot-like activity, but it's chatbot built specifically to answer questions about a design tool and the design that's currently in progress, that's being progressed or processed by that tool. So all of our implementation solutions are getting chatbot updates. Some of them are actually in production, but suffice to say, by the end of the year, the entire product line will have this capability. Level 3 involves complex reasoning. And some of that is in the technology, the code generation technology that I'll talk about today. But again, this is the first step on the way to kind of this fully autonomous kind of environment that we're all kind of shooting for. So that's kind of the journey. I'd say check the box here. And where we are today is we're adding conversational LLMs, and we're operating kind of somewhere between 3 and 4. So we're making progress on the journey. So kind of digging into the technology in a little bit more detail. What this describes is kind of at a very high level the architecture of the solutions that we're delivering, right? So first, all of our individual point tools, and this is basically just a listing of all of our point tools, everything from verification tools and conformal to implementation tools and so forth. But they're all getting MCP interfaces, and that's just a standard way to kind of talk to tools in an agentic environment. Now, at the center here, we see this Cadence JEDI platform. What is JEDI? JEDI stands for Joint Enterprise Data Exchange and AI. So it's a big data solution, but it's also got AI capability because this is essentially the thing that manages the LLMs. And so for our solution, while our solutions use LLMs, we are not developing, and we will not enter the whole foundation model market. It takes billions of dollars to develop and maintain those things. And there's just a lot of activity already and a lot of spin going on. So rather than reinvent the wheel, we have APIs that can talk to foundation models, and we leave the choice of foundation model up to the customer. And that's important too, because with the rapid pace of change, these things are kind of leapfrogging each other, and it's unknown, say at the end of the year, which of these foundation models are going to be better. So we leave that choice to the customer. The customer can easily kind of switch to the latest and greatest. Whether it's on-prem or off-prem, it really doesn't matter to us. That's a customer decision. And then the other part of the solution involves how do we extend the set of knowledge that's understood by these LLMs to pick up things that are just not out in the public domain. For example, none of our product documentation is in the public domain. And clearly, the designs our customers are working on are not in the public domain. So we need ways to kind of extend the knowledge set, and we do that through MCP interfaces, and we can tap into Cadence knowledge sources, so tools, documentation. We maintain a lot of documentation on kind of errata, and then customers have various data sets as well that they want to tap into. But net, the solution, the architecture allows us to apply. It can be applied to any of our point tools, and it allows the choice of LLM by the customer, and we have a way to extend our knowledge set beyond that was learned by the LLM. Okay, so switching gears a bit, let's kind of dive into the product details. So Stratus high-level synthesis solution is a key portion of the Cadence code generation offering. And if you're not familiar with high-level synthesis, I'll take a couple of slides to kind of just walk you through what is it. When I talk about high-level synthesis, what does it mean, right? So let's walk through a real simplified process, and we'll start with just kind of a code snippet. This is a C++ function. It's super simple, right? We've got a few unsigned variables, and then what the function does is output one is just simply temp1 times I4, and then output 2 is temp2 plus temp3, right? So the first thing we do when we encounter a function is we read it in, we elaborate it, right? We turn it into a control data flow graph. And this gives us some understanding of the dependencies. Now, the next step in this process, in the high-level synthesis process, is to do what we call characterization. And by that, I mean we characterize the big stuff. And here the big stuff are these arithmetic operators, but we also do things like muxes and so forth as well. And the goal is to, when we say characterize, we actually run those through synthesis. There's a integrated copy of our logic synthesis solution, and that gives us the ability to kind of map it and optimize it, map it to a technology, a specific technology, and then optimize it. So we know what the operating range is. And operating range means like, delays, what's going to be the area, and also what's going to be the power consumption in some cases, if you're interested in that. So we get something like this. So now we have an updated control data flow graph, and we know this multiplier has a 1.2 nanosecond delay. The adder has a 0.65 nanosecond delay, and so forth, right? And you can see where the area is, over 2K square microns. So we're beginning to kind of get a physical understanding and a temporal understanding of what this function is capable of doing if we were to go ahead and implement it. Now, the next stage of the process is, because this is just a function, right? It's basically saying these are these are the input, these are the outputs, and this is the function that maps the inputs to the outputs, right? The next stage is to actually schedule this. If it's going to run in hardware, it's got to have a clock, it's got to have some real signals and so forth. And so what we do is we use the information gleaned from characterizing it to know where we can, essentially insert the clock edges. So if you've got a 2 nanosecond clock period, that means, hey, we can pack this multiplier within that stage, because clearly 1.2 nanoseconds is less than 2. And down here in the second stage, we've got this adder, which is 0.65 nanoseconds, and it feeds into a multiplier 1.1 nanoseconds. The total delay is 1.75 nanoseconds. So it fits well within our 2 nanosecond clock period. So we do that, and this, again, simple example, but we do that throughout the circuit, and that kind of gives us an understanding of where we can insert clock edges. And once we have that, then we can now generate the RTL. There's a lot more that kind of goes on in the way of optimization, but the simplified process is read and elaborate the source, create the CDFG, characterize the operators, and then schedule the design, and then write out the RTL. That's essentially HLS in a nutshell. Okay, why is that important? Okay, and why is HLS? Why has it been widely adopted for DSP and algorithmic designs? Let me try to answer that question with this slide. And this shows an IIR filter example. This is just some code that was lifted off the internet, right? But if you look at this code, and you start going, okay, well, where are the kind of arithmetic operators? And I've highlighted those with the red circles, right? And note, these things are within loops. So, a loop by definition means it's going to get executed, many times, right? So if we try to map that to a table where we want to understand what the solution space, the hardware implementation solution space range looks like, and this is a common exercise. If you're trying to build hardware, then you got a finite number of resources that you're, implementing engaged, right? So that's important. So if we take this code and we unroll the loops, then the largest implementation will be all the loops get unrolled. And you can see, if you do the math, you get 45 adders, 24 subtractors, and so forth. We have a total of 138 arithmetic resources. Now, that's one end of the spectrum, the big end of the spectrum, the largest. The other end of the spectrum is the smallest. So if we keep the loops intact and we just count the number of arithmetic operators, we wind up with 5, right? And this means that we're going to share these things, which means the hardware actually has to have, kind of caching, decaching intelligence to handle intermediate results. And it's, you've got muxing as well that needs to be done in order to implement this, super efficient 5 resources shared across this entire algorithm. Now, there are a whole range of kind of solutions that are in between the largest and the smallest. And that's essentially the job of the HLS tools, to traverse this, which is essentially a 3D surface exploration job, right? You've got area, performance, and power being traded off. That's by definition a 3D surface exploration problem. So the reason people use HLS to do this versus manually, if you were to do this manually for every single one of these points in between, you've got to write the RTL. You've got to go through some level of functional validation to prove that it functions correctly before implementing it, right? And then you've got to go through logic synthesis to understand what the power, performance, and area is. Um, each of these implementations would take on the order of a week, and so exhaustively exploring this solution space, there simply aren't it's not enough time and resources, right? So that's why people are using HLS for these kind of DSP and algorithmic designs. This is precisely what Stratus does. Okay, so when I look at Stratus in the context of a flow, because remember, our customers are not trying to do HLF, they're trying to do digital design, right? Then this is kind of what it looks like. I set the tool up and I tell it, hey, what are my, if I want to map this thing to gates, what synthesis tool do I want to use? Do I want to do any power analysis? But you're setting up the ancillary tools that are all kind of integral to the flow. And the next thing you do is you configure those, you configure what runs you want to make. So for example, if you want to explore, clock frequencies ranging from, half a gigahertz to a gigahertz, right? You can tell the tool to do that, and you can tell it to increment the clock frequency by, I don't know, 10 megahertz or 100 megahertz or whatever the case may be. You set the tools up, you configure the runs that you want to make, and then you kind of fire and forget. And the process that Stratus goes through is it first does that HLS or high level synthesis that I showed you on the previous slide, where it elaborates, characterizes, schedules the designs, and writes the RTL. But it first does that step, then it goes and simulates it to ensure that things are functionally correct. Now, there are additional steps that you could insert here. So if you're working at an advanced node technology where physical effects cannot be ignored, even in the front end, then you can add additional steps like floor planning and physical synthesis to give you a more accurate view. And all this information is stored in a metadatabase, and it's actually fed back into the HLS solution to be used in subsequent design refinements and subsequent runs, right? At some point, you're going to need to analyze the results and know that Stratus has an IDE that's purpose built to help you make sense of machine generated RTL versus a system C specification that drove the creation of that RTL. So you can do things like cross-highlighting from the different design representations. So clicking on an element, say in a CDFG graph, and having it link back to the system C source or the RTL. These are all supported. You can click on, there's a rich set of reports, and you can click on things that are in the reports and have it take you back to the design and the design objects that were responsible for creating those report entries. So again, the full environment is really important, and Stratus supports automation of the flow, or well beyond just high-level synthesis. So before diving into this Stratus AI piece, I do want to give you a sense of kind of how we got here, where we've come, because that's important, because it shows what we're focused on, and should also kind of give you some indication of what we're going to be doing in the future as well. So when it comes to chip design, everything is really driven by this quest for lower power designs that perform much faster, right? And they can be built with less effort, less engineering effort. So power, performance, and productivity. Area optimization is also important as well, but these kind of dominate the equation today, right? And so what this slide shows you is over time, what have we done, going all the way back to 2022 to improve these on these three technology drivers. So in 2022, out of the realization that a lot of our customers' designs started in MATLAB, and our customers are doing signal processing designs, DSP designs. MATLAB is almost a de facto industry standard for doing that kind of design work. And so rather than have our customers translate from the MATLAB world into System C, we work with MathWorks to create an automated flow where you're in MathWorks, you're developing your design, you're simulating your design. You can now write out a Stratus project where it spits out the System C. And from that point, you can do all the optimizations that I kind of mentioned earlier within Stratus. There's a lot of kind of work that's been done in AI, ML optimization. I mentioned the product Cerebrus. This is our reinforcement learning solution. We released that in 2023. It's been widely adopted. The other thing we did in 2023 was we automated this power shutoff. And so everyone's concerned about lowering power. And so if you have idle functions that are on a chip, the common industry practice is to actually shut those off, to actually turn them down. But when you, as soon as you shut something down, you have to do it in such a way that it can be woken up and woken up efficiently without going through a whole reboot. And that involves specifying some retention registers that save the state. So we have an automated way to do that because we have an intimate knowledge of state within Stratus. So 2024, our sister group, our verification team, released a formal verification solution that allows you to formally verify, right, through mathematical proofs, the RTL versus the system C. And so the problem this solves is with DSP designs, it takes a lot of vectors to actually simulate some of these functions, right? And so if you're relying on dynamic simulation to verify functionality, you're either going to have a very long wait, or you better purchase like some kind of a hardware emulator to speed up those simulations. And so what formal verification solutions do is they're just a much more efficient and exhaustive way to prove that two things match. In this case, system C versus RTL. Now in 2025, here we're getting kind of close to this where we are today. So we did this C++ flow release, and this allows. We discovered a lot of our customers were modeling in pure C++. They had an aversion to using system C because as soon as you go that route, you're carrying around the system C kernel, and your simulations tend to slow down by a couple of orders of magnitude. So we can now support pure system C design, and we have a way to kind of automatically convert that into system C and run it through the Stratus flow to give our users PPA visibility. Okay, so this is also important because this is also a key portion of our Stratus AI products. The first one was released in December of last year. The next one's due out mid this year. Now, Stratus AI, again, we're adding an LLM to the equation, and so it actually changes the way that users interact with our tool, but it also adds code generation capability. So let's talk about Stratus AI. Now, when we first kind of set off to do this, like a lot of people are today, we thought we could possibly do it just having the LLM write RTL directly. And what we discovered was the times when the LLM was actually able to create functional code was so low that essentially the solution was rendered useless. And so if you go and you start poking around, you look at some open source benchmarks, you'll see even the best kind of LLMs, they're only able to create functionally correct code on the order of like 60% of the time. And if you're doing chip design, that means 4 out of the 10 things that you try are bad or useless. That's not a very productive way to kind of go about things. So when we dug in, what we discovered was the root cause of why LLMs can't directly produce RTL that's functionally correct. Forget about PPA. The reason they can't produce functionally correct RTL is because there's not enough RTL in the public domain. Our customers don't put their designs in the public domains. Their designs, this is core intellectual property. It'll never show up in the public domain. So, until that problem's solved, this essentially, it won't work, right? The other problems with this direct approach is how do you interprocess technology information? If you're talking about, a natural language prompt, somehow in that prompt, you've got to make that prompt timing aware, power aware, right? It's got to understand like where the clock boundaries are going to be, but there's just a lot here that's not addressed by LLMs and natural language input. Not to say that you can't, but today these are not covered. So if we look at Stratus actually covers all the deficiencies of this direct approach. And when we combine the two, we can leverage LLMs for what they're really good at, producing functionally correct C++ code. And then we can leverage Stratus for what it's really good at. It reads a technology library, it reads the constraints, and it's got purpose-built optimizations for crafting the microarchitecture that's designed to hit and meet those constraints. So this is essentially the solution that we're bringing to market. So going another level of detail down, it looks like this, right? So the goal is to use the LLM to generate hardware-friendly C++ code. No, even this piece, what we discovered was we had to do some prompt engineering because if you take so LLMs, the quality of the output is highly dependent upon the quality of the input prompt, right? So based on our understanding of what needs to be done and how these LLMs work, we don't actually feed the user-generated prompt to the LLM. We take that and we modify it as necessary, and that we've seen improve our results markedly, right? So the LLM produces the C code, and then we take the C code into Stratus HLS, and again, it's driven by inputs like the technology library and the constraints. And then we inherit all the other stuff that you get with Stratus as well, like this environment that I discussed that purpose built to allow you to make sense of machine generated RTL, right? And then the other things you pick up, I discussed with flow earlier. So all of those additional kind of adjacent flow components, they're all inherited. So our solution kind of hits the ground running, being essentially functionally complete. Now, the goal of this is productivity, PPA, and flow automation. Okay. And so as you start looking at other solutions and technologies, right? What's amazing is kind of the dearth of information on PPA. Everyone seems to be focused on, hey, can I generate functionally correct code? That's only part of what an RTL development engineer does. What they're really doing, where they spend the bulk of their time, is they're designing a microarchitecture and they're expressing that microarchitecture in Verilog RTL. And then that, oddly, it's just not discussed right now, but it shows you where the state of the technology is. So these are our three goals. And so important to be able to measure those. And so I'm going to kind of walk you through what the solution looks like, and we'll take a look at some numbers, some early numbers, again, based on real design activity. Okay, so I mentioned this chatbot changing the way that our users interact with our tool. And what this slide shows is what that looks like. Okay, so here a user can just input a query or a prompt. In this case, I said, create me a system C function that implements a FIR filter, right? And you give it some details about the inputs. In this case, I want 8-bit input values. And then in more detail. And so what the tool then does is it takes that and actually generates the code, right? So you can take this code, you can actually refine it. There's a refactoring mode you can go into where you go, okay, I don't particularly like this particular for loop because I want to change it in so and so way. So you can actually highlight that section and tell it to incrementally modify that portion of code. So refactoring is a big portion of what designers do, because design at core is very, very incremental. So another example of interacting via this chatbot, and this is a case where the user is just trying to understand how I would do something like pipelining, but within Stratus, right? So just, hey, explain how pipelining works. And so rather than have to go to a document to do that, the tool actually spits out. It's actually getting this information from the documentation, right? But it's giving you a very concise kind of answer to the question that the user imparted. And it's also giving you a line of code that you can inline into your code to control pipeline. So very efficient user interaction. So I mentioned quantifying, productivity and quantifying some of these metrics that we measure goodness with. So the LLM is largely responsible for the code generation productivity piece, right? And so how do we measure productivity in that kind of a world? Well, speed of generation, right? And so here I show like 7 designs. There's a most complicated being an AES encryption engine, but there's a FIR filter as well, and you can see some other smaller functions, right? And the generation times are pretty quick, right? So 6 to 10 minutes for this AES. I'm not sure why there's a range. I think the range is sometimes it takes longer than other times, right? And that's just kind of the nature of LLMs. But you can see we're literally minutes to generate these functions. Lines of code, C++ when it comes to describing functionality is fairly compact, right? So you'd expect to see that. But the real understanding of the productivity gain comes when you start looking at lines of RTL, because this is directly analogous to what a user would do manually in the absence of this technology, right? So in this case, the AES, it took about 10 minutes to generate the C code, took about 11 minutes to actually do that optimization and RTL production. So 214,000 lines of RTL, produced in about 21 minutes. That's a staggering amount of productivity. And that's why we're doing this, and that's why the whole industry is kind of looking at ways to kind of, make this technology work because the productivity gain is really kind of off the charts. The potential productivity gain, I should say, right? Now, I've been harping a lot on PPA. Why? Because our customers harp a lot on PPA. That at the end of the day, that's really all they care about, right? And they're even willing to invest additional energy to achieve PPA, but it's clearly priority one, right? And so the beauty of the solution that we're bringing to market is we inherit all the PPA goodness of a production solution that's been in production for close to 3 decades. Now, what this slide shows is we're looking at area, power, and design time for a range of designs, right? And then a range of designs and design types, right? In some cases, we're competing against hand-coded RTL. Here's a case we're competing against a commercial IP that the customer was looking at adopting. In other cases, we're competing against competitive high-level synthesis solutions. But when we aggregate all of these results, what you see is Stratus delivers excellent PPA. So on average, we can reduce our customer's area by 24%. We can reduce power by close to 50%, and the productivity is 4x. And this productivity figure, that seems huge, but that's been the story of EDA. And new technology is almost defined by these kind of gains, right? We're all in this quest for the next 10x, right? And so this is one component of our ability to kind of get there. So check box on the productivity side, right? Literally being able to do hundreds of thousands of lines of code in minutes, and then also check the box on the PPA side as well. This is built on a foundation of proven in production technology. Now, when I talk to customers about this technology, there's kind of this uniform fear of code generation solutions. And why is that? Because there's been a number of code generation solutions, over decades, and they've all had kind of one problem in common, right? And that is debugging code that you didn't write is significantly more difficult than debugging code that you wrote. So there's this fear that, the LLM is going to generate this code, it's going to have all these signal names that don't make any sense, and the structure is going to be unreadable. And if it breaks, I will not have the ability to kind of fix it. So clearly we encountered that with just traditional Stratus HLS, and we invested a lot of energy into this IDE. And this is kind of a glimpse of it. I've kind of touched on this earlier, right? So managing multiple implementations. When you're talking about high-level synthesis and this class of solutions, you're really looking at exploring the solution space, which means you're going to have to compare multiple implementations. And so we've got a way to do that in this particular pane. You can see we've got a number of different kind of implementation configurations. You can click on those and they'll produce reports, and we can compare different configurations or results in these reports. And then the ability to kind of be cross-highlight and click on RTL or graphical objects and have it take you back to the RTL or back to the system C. So links to source is a key component of the solution. But suffice it to say that, again, because of our experience in this area, this is not a question mark. It's proven. We have proven the ability to kind of deliver solutions that make it easier for our customers to debug machine-generated RTL. Now, going down the next level of detail, all of this stuff is going to sit within the context of a flow, right? And so a question that we always get asked, and at root of it is this fear of LLM hallucinations, just the raw technology, the core technology, there's this random step, and that's kind of the source of hallucinations, and that's not going to go away anytime soon. And so while you can live with a certain amount of imprecision when you're, creating text, hey, write me a story about a dog that goes to fish, right? You cannot tolerate imprecision in IC design. And so the answer to that today is verification. So if I'm a human, humans are notorious for imprecision, for producing results that are imprecise or erroneous. We get over that because we verify everything, right? So the same is true in this environment as well. And so what this slide shows is the steps, starting with C code generation, right? I start from my prompt. The system generates some C code. I then verify that C code running a test bench, and the test bench has to be user supply. Now, no, outside the scope of this discussion, but our sister verification group is developing similar technology that automates verification. So think of an LLM, but tasked with creating a test bench that'll test out some function, right? So all these things are happening in parallel. And so suffice to say, a year from now, a number of customers are going to have code generation solutions that are LLM based and verification solutions that are also LLM based. And so this whole thing will be much more automated. Okay, so the C code is generated. The next thing we do is we wrap that, turn it into System C. What is System C? Essentially, it's a class library for C++, and it defines things like signals, resets, right? Clocks, things that aren't defined by the general purpose programming language C++, right? So we wrap that, so the signals and all the hardware constructs are now defined. We can now take that into high-level synthesis, where we first impart the constraints, and then we actually run it. And then, similar to these steps that preceded, verification is also a key piece of what happens after you produce the RTL as well. Now, if you do this correctly, then you can have one test bench that's used against all of these different abstraction versions of your design. Now, when you talk about high-level synthesis and this class of solutions, especially DSP circuits, then you're going to be mucking around with things like latency, right? So one implementation may have a very different kind of latency than another implementation. So your test bench has to be written such that it's insensitive to that. And usually that means there's some kind of a handshake where you say, hey, this data is ready. And then you can now go and test that data. Right? So there's a handshake before you actually start checking things. So that's kind of the flow. So our first version was really focused on the C++ code generation for the high-level synthesis market. And many of these tasks are not automated. So our next version will automate much of these things. And I'll talk about the differences between the two versions on some subsequent slides. But let me walk you through a demonstration of the version 1. Again, this went into production in December of last year. But let me give you a feel for what this looks like if a user's gonna go on.
In this video, we will demonstrate Stratus AI. It adds LLM-based functionality to Cadence's technology-leading high-level synthesis product, Stratus HLS.
Can everyone hear that
The
audio, by the way?
demonstration will show the creation of a 2D convolution filter from a natural language prompt.
Yeah, Jeff, we can hear it.
The use of AI to refactor the generated code to make it simpler, and the ability to automatically import the AI-generated filter function into the high-level synthesis environment. We'll use the Stratus analysis platform to compare the PPA of a pipelined and an unpipelined implementation of the filter. This is the Stratus integrated design environment. At the right is the Stratus AI window, including a pane for putting in prompts and a pane for seeing responses from the AI system. Let's put in a prompt to generate a 2D convolution function. We will specify the inputs, the outputs, and the data types to be used. Wait for a moment while the AI system generates the function for us. There we go. The response pane shows us the generated function code along with an explanation of the generated behavior. It's up to us to inspect this and make sure it meets our requirements. Otherwise, we may want to try again or adjust our prompt. This looks good, so we'll go ahead and save the contents of the code bubble in the response window to a file. There it is, convolution.h. The question mark colon mechanism used to clamp the results to the size of the output looks a bit old-fashioned, so let's get the AI to clean it up for us. The context menu in the editor has a couple of AI-related options. Explain can be used to get an AI-generated description of the selected code. We'll use modify to prompt the AI system to simplify the code using a clamp utility function. Wait a bit for the AI to process the request, and we see the result. The right-hand pane shows us the proposed modification. The left-hand pane shows us our unmodified code for comparison, and we get an AI-generated summary of the modification. This looks good, so we accept the modification, and our file is changed. The next step is to take this convolution function and make it synthesizable so we can produce RTL. To do that, we'll add a module to the project. The module contains the hardware I/O structure and the protocol. The import goes ahead, and we can see that our project has a new convolution module and a default HLS configuration. Of course, once we import the module, we can easily explore different architectures. In this case, we've added a pipelined architecture. And we can run logic synthesis, power analysis, etc. Here are the results from running Genus logic synthesis on the RTL for the pipelined and unpipelined architecture of our AI-generated convolution filter. In this video, we've seen the high-level synthesis capabilities of Stratus combined with leading-edge AI to provide a productive assistant for experienced Stratus users, or to give users new to HLS an easy way to get started with this technology. And whether you start from prompts or any other high-level input, Stratus has proven to deliver production-ready RTL for advanced designs over billions of delivered chips.
Okay, so that was the demonstration. Now, to kind of round things out, I mentioned kind of adjacent technologies. Now, when you talk about writing RTL, verification, or functional verification, and writing an RTL go hand in hand, right? Meaning that those two tasks are kind of done simultaneously, right? So I'm in our implementation group, and so this product is really focused on how we implement things. I mentioned that our verification team is also using AI and developing, products that are AI assistant. So we have something called, front-end silicon agent, and we actually announced a product last week called ChipStack, right? And the whole purpose of this product is to use AI to develop verification collaterals, and so to essentially accelerate the productivity of your whole verification activities. Now, what this shows is kind of the different stages of the overall solution. Some of the things that kind of stand out are, there's a VS Code integration. We're seeing a lot of kind of uptick in the use of VS Code because of its Copilot integration. But Stratus AI is the code generation engine within this front-end silicon agent as well. And so, one way to think of how we cover the verification space is you've got one kind of common engine that's responsible for generating Verilog, and that can be used to generate Verilog for verification as well as Verilog for implementation. So commonality among the generation solutions. Now, from a production availability perspective, kind of rehashing some things I said earlier, this phase one. Now, no, this is a functionally complete system, right? It has the ability to generate C code. We can, then generate RTL by taking that C code through Stratus. So it begs the question, well, how is this any different than the one that's coming in phase two? Well, phase one was really focused on high-level synthesis designers. High-level synthesis designers have no qualms about, C code. A lot of the algorithms that they design are in C, right? Whereas if you look at RTL designers, generally speaking, they don't want to see C. They need to see the reports and the analyses for their designs, but they want all of that kind of RTL-centric or Verilog RTL-centric as opposed to C code. So there's a bit of abstraction that's kind of going to be done. So more analyses tools to kind of give the designer things like PPA information, but not necessarily with respect to the C code, more RTL oriented analyses. So that's kind of what we've got in store and under development. At this point, I'm happy to take any questions that you have on anything that I've discussed.
Thank you so much, Jeff. Wonderful presentation. I really appreciate all the details that you've shared. This is wonderful, actually, for our participants. I'm sure they're going to really take advantage of this opportunity to leverage Cadence tools. And with your presentation, it's like very clear what the flow is and how to better utilize these tools to get to a final product and outcome that is really the best that you can get out of the tools. So thank you so much for the presentation. So for the participants that are here online with us, if you have any questions, you can put it in the chat or you can possibly unmute and ask your question. So feel free to do so. We just give you guys a few minutes to get your questions ready and ask.
Oh, so there's a question. Which software was used to create the presentation slide? It looks really cool. The AI HDL thing also makes very impressive. So let me say this in a diplomatic way. We have AI, like we use Copilot. Copilot not so good at creating PowerPoint slides. I would like it to be, but every time I try, it just somehow just fails miserably. So these were all, unfortunately, I was not able to use AI to create these slides. I've heard some other solutions, like Claude, for example, are better at PowerPoint slides, but we don't, within our company, we don't use that. So
Also, something to add, when you're with a company, every slide you make has to go through layers of approval. So a lot of
well,
changes need to be made, I'm sure.
yeah. Well, in this case, this is in December. We did like a road show
Mhm.
in China, so Beijing and Shanghai, and this was part of just an overall focus on AI technologies within Cadence solutions, and so that's where this content comes from.
Wonderful. So the question I have in the chat is, are the tools free? If not, there are any opportunities for students to access them? Yeah, so I answer that one briefly, and I will let you guys probably add more to it. So the tools are not free. Of course, there are licenses that Cadence works with universities, and they have a ongoing partnership with many institutions around the world, and who are using the licenses. And if you're part of those institutions that have the licenses, you can access the tools through your institution. However, what we're working on with the Cadence team through the competition is to be able to provide you with access to some of the tools that are useful for the competition for the duration of the competition. And the more details on that will come next week. So we're, figuring out the final details of that. And your mentors are going to be the ones that will help you guys, get a good idea of how you can access and use the tools. So we have that meeting set up next week. We're going to work with Cadence team and we'll release more information once they become available. Anything to add, Jeff, to that?
Yeah, there's one comment about, if I use a public AI tool to generate RTL, can I port that to Cadence tools? So there's a whole set of tools that I didn't discuss that are involved in taking the RTL and implementing that. So logic synthesis tools, place and route tools. So those logic synthesis tools, they can take RTL from any source. So whether you hand created it or created it with Stratus or created it with a public AI tool, it doesn't really matter. They ingest RTL.
Thank you.
Let's see. I used to
Here's
think,
another one.
RTL being fine-grained compared to what HLS would generate. How is it that the tool can generate codes that are faster than hand-coded RTL? Is there a specific stage that makes Excel compare? Okay, so that's an interesting and good question, right? How do we beat hand-coded design? So there are a number of reasons we consistently beat hand-coded design. So I mentioned exploration and that 3D surface exploration problem. So if you were to count the number of versions of a design that a human would have to create to adequately explore the solution space, humans rarely have that much time. You can't create like 10 versions of your design and then synthesize them and understand what the PPA is. You simply don't have enough time, right? And so if I can use a HLS tool to rapidly produce different microarchitectures, then I have more than I can explore, right? And so that alone is the answer to the question how we're able to beat hand-coded design, because we can do it much faster, therefore we can explore more points, and we can find the point that beats the handcrafted point. Because typically we're comparing against like one point in that solution space, and that's the handcrafted. That's whatever handcrafted design the user created. May be good, may not be good, right? The other way that we're able to beat hand-coded design is if I'm creating RTL, and remember, I'm really designing a microarchitecture. I'm making design decisions based on estimates at best, guesstimates are probably more accurate, right? Because I can't map this thing to gates in my head and run a static timing analysis on it to determine whether or not this move is good. So I'm guessing. We don't guess in Stratus. We characterize, we synthesize to gates, and we analyze what the true power, the true performance will be. More accurate decisions lead to more accurate outcomes, lead to better outcomes.
There was a follow-up on that as
Okay.
well.
So AI has a single point of contact at the beginning stage. Is there a way to leverage to improve in the DSE part, design space exploration part? So yes, and this is more towards the agentic flow piece, right? So you can picture like this agentic flow that spans RTL creation, logic synthesis, and say physical implementation. So if, for example, the whole flow is under agentic control, you get to a point where in physical implementation, for whatever reason, you're not able to close in your constraints. In that system, you may go back to this RTL generation step and say, hey, generate me some different RTL because I've run into this particular timing problem here. And that's the beauty of this agentic control flows. It's just like manually controlled flows. We often go back reluctantly because it's expensive. These agentic flows will be able to do the same. Okay, next question. In this
Thank you,
AI
Jeff.
era, which languages should we excel in? C, C++, System C, Verilog, System Verilog. Could you
I
share?
would say English.
Well, and actually not limited to English anymore as well, right? There's no
Right,
reason.
right, absolutely.
Yeah. um, so it's a very good question as well. So we see C and C System C being used largely for system level descriptions and algorithmic descriptions, a lot of DSP design work. I don't even with these LLM generation solutions, because they're focused on natural language input, I just don't see C being widely adopted on the hardware side. And so if you're talking about hardware design languages, you're really talking about HDLs, and that's Verilog, right? And System Verilog. I'm not sure that answered your question, but I mean, part of the question
That was
ties to
perfect.
do you need to know a language anymore, given the LLMs are going to produce all
Right,
this? I
yeah.
think the
I
answer is
mean,
yes,
with
because
AI, it's really challenging, right? So Of course, knowing fundamentals are still valuable because if you don't know fundamentals, as you said, Jeff, part of your talk, but when you write the code, of course, finding the bug, understanding it could be easier. Whereas if you didn't write the code and you don't have the necessary background on that programming language, it becomes exponentially more difficult to identify what could be wrong. And sometimes there could be no bugs in the code, and like the code is functional and everything works, but there are still issues. There's still things that you can optimize. And if you don't have that understanding, it becomes challenging, in my opinion, to do those optimizations. Of course, AI can help, right? You can just, have a conversation, go back and forth. Agentic AI definitely is a good approach and a good solution that could sustain, down the line. It could improve and get better, right? However, I think at least from what I see, you still, if you have the fundamental knowledge of those programming languages, even one programming language, makes a big difference.
Yeah, exactly right. Um, and to some extent, you could say it's even more necessary because these are leverage solutions. They're going to give a single designer the ability to do so much more. But when things don't go right, you need to understand what they're doing. And if you don't have that kind of understanding of the base languages, what do you do?
Absolutely. Any other questions from our audience that we have in the webinar? And obviously, there's more opportunities to ask questions later on, and we'll be in contact with Jeff and the Cadence team. If we can answer the questions, we'll be happy to do so. If we need to go to Cadence team, we'll have to do that, and then we'll get you your response and we'll share it in the Discord channel. So stay tuned on the Discord. If you have any other questions that we don't get to it today, feel free to post them on Discord, and then we'll be in touch with the Cadence team to get your answers. Of course, this webinar is recorded, so if you're watching the recording of this webinar, same thing applies. So please send us your questions in the Discord channel for the competition, Harvard Design League, and we'll be able to get you your responses. Any other questions from the audience? Maybe a couple more minutes here. Sometimes it's, you need to give time to people to think about the questions, and all we have is time right now. So happy to give them the time to work on this. In the meantime, I do want to thank again our Cadence sponsors and presenter Jeff here today, and also I see Benjamin, who's been a key for helping us get this partnership with Cadence and getting access for you guys to work with the tools that traditionally might not be available to many students. So this is a very unique opportunity, and we're excited to bring you this opportunity with the help of our great collaborators at Cadence. Question in the chat: could you also suggest how I can excel in digital design? I believe it is very important regarding AI. Any thoughts?
So I think part of I'm delighted to see what your professors are doing in the way of exposing you to AI today. And I guess my advice would be lean into this technology, right? Because it's moving at such a rapid clip. To the extent you embrace it and become really good at using it, then you're going to have an advantage over those who don't, right? And so, if you look at Cadence and kind of where we're going, AI is everywhere, right? And then we're not kind of doing it haphazardly. It's very it's appearing in places where it's delivering better PPA, better productivity, right? But again, lean into this technology because despite all the hype in our space, it's producing incredible results.
I couldn't agree more with you, Jeff. I think it's really key to learn how to properly use these tools to be more efficient at what you do, be more accurate at what you do, and get better outcomes in short amount of time. Of course, um, let's say if you're trying to start a company, being like a chip design company, you know, it's a race, right? So you have to be able to get to a design that is functional, secure, and reliable in a short amount of time. And you know that becomes a product that you sell, you make revenue. But then that cycle, if you can get your design time to be shorter, meanwhile yield a better design and yield a better, more reliable and more secure design, then you actually have you can excel in what you're doing and you can get ahead in the game, right? So that the tools at your disposal is just learn how to use it properly, and the rest is just the effort that you put in. I see there's a link in the chat that Benjamin shared. It's the Cadence learning maps. I will make this also available on AI HDL website under educational resources so you have access to it. But I highly recommend you guys going over and taking a look at it. It definitely has a lot of useful information to get you guys started on using Cadence tools.
Hi Jeff, I have a question. So regarding the Stratus Flow and the Stratus AI, I was curious if there were any hallucinations that were present during the HLS to RTL generative stage, or are there any tools to know how I can check whether my code is secure or not?
So on the HLS to RTL generation step, we don't use LLMs for that.
Hmm.
Okay. So that's there are no hallucinations, and it's 100% deterministic.
Okay. Other than that, are there any tools to check how secure my code is, like my RTL code or my C++ code?
From secure from a hacking standpoint, or
From a hacking standpoint, yes.
yeah, I'm not as familiar with that set of tools. I do know there are solutions out there, but it's just outside of my kind of area of expertise, and not something that we offer. I offer in my products that I'm responsible for.
Thank you.
You. And then I'm going to briefly share my screen to go over the website and then show you where you can find more information. All right, let me bring this down here. All right, let me see if I can share my screen. Hopefully you guys can see my screen.
Yes, Professor.
All right, wonderful. Yeah, so this is the AIHD website as you guys are familiar with it. So if you're not sure where to find more information on the Discord, there's a link to Discord here. On the top of the page, you see educational resources. If you click on that, it will take you here. You open this tab. You have access to all our tutorial webinars that we had before the competition starts. We have tutorial for open source tools. We also have the design phase documentation examples. Down below, you see Cadence. So there is a full RTL to GDS demo using Cadence tools. I'll have to update this link. There is onboarding curricula, so you can see all this information here. There is the learning maps that was just shared. You can see that here. And we have the Cadence courses that you guys have access to right here. So there's a lot of information here regarding the tools and also more information. for you guys to take advantage of. There's also some other material on like videos and YouTube links. So feel free to take a look and let us know if you have any questions. If no one has any other questions, then I think we can thank our speaker, Jeff, again for presenting today, and thanks for sharing all the amazing information about the tools. And hopefully,
Thank you for having me, and thank you for your time and attention. I appreciate the very insightful questions.
of course, thank you so much, Jeff, and thanks, Ben, as well. For the remainder of the time, I believe we can be online if you have any questions from our mentors that are available. Hopefully, we can get those answered. Maybe like another 10 to 15 minutes for us to stand in line. But Jeff and Ben, feel free to drop off. Thank you again.
Thanks, everyone. You guys have a great day.
Have a great day. Bye bye.